All right, welcome. So in the last video, we had a chance to take a look at the bubble sort algorithm and prove it correct using two loop invariants. I want to continue with the analysis now of bubble sort by now looking at the number of operations that are carried out by the bubble sort algorithm on an input of size n, or more concisely, a runtime analysis. So let's go ahead and do that. So for convenience, we're going to continue using the same pseudocode that we used in our proof of correctness in the last video. This is common when you're going to prove an algorithm, although every once in a while, as I mentioned in the last video, we usually design our pseudocode for the purpose that we have at hand. And so the purpose we have at hand right now is runtime analysis. And so if there was maybe a minor change here or there to the pseudocode that would simplify our analysis, then we would usually do that. Now, of course, if we want to pair the proof of correctness we just did with this runtime analysis, meaning they're for the same algorithm, we want to minimize the number of changes we make between the pseudocode between our analyses. And if we can get away with no changes at all, like I've done here, that's usually considered to be the best case. And when we're going to carry out the runtime analysis, we're going to again use some of the same tools that we were looking at in earlier videos. We're going to start doing a line-by-line analysis. This is following sort of a strategy of divide and conquer, which is prevalent throughout computer science, which is if we want to know, how many operations the whole thing takes, well, let's break it down into little pieces and figure out how many operations each piece takes and then put them back together. And so that's our strategy here. We're going to start by doing line-by-line analysis, and then following what we did again in earlier videos is we're going to use summations to express the number of operations carried out by the loop structures that we have in our algorithm here. And again, we have two loops here, two for loops, and they're nested. That means we're going to actually end up with a nested summation. Okay, so to begin, I want to, as I mentioned, do this line-by-line analysis. So let's just take a look at what I've got here for my estimates for a line-by-line. How many operations are carried out on each line? Again, we did this in an earlier video, so I'm going to go a little bit quicker with this one here. The first line I'm just counting as entering the method, entering this algorithm, which usually takes at least one operation, and I'm going to call it one operation for simplicity. On this line, I need to count operations. Now remember, this line is a special line because it's sort of this line determines the looping structure that we are entering, in this case a for loop. And we know that this line is actually executed more than once, and when it is executed more than once, maybe something different happens each time we come here, or specifically, the first time we come here, we do some initialization, and I've got that stated here as an assignment, and then the next time we come around, we actually increment that I value. So I'd say the second time, either one way or another, it's going to count as one operation. So I sort of lump those two together because it depends what iteration we're on, but we're going to do one or the other of these steps. What are the other two operations I have here? Well, at least the naive way we might compute this, we have to do this -1 every time, and so that's a subtraction. And then we also do one comparison where we compare I to this terminating value to see if we should terminate or not. So that's the comparison I have on there. And that's the same idea we had the first time we went through looking at loops. So when we look at the nested loop, it's effectively the exact same thing. The code is a little different. We have a J and we have a -I and such, but the actual number of operations is exactly the same. We're doing the same effort on to initialize this loop. Now, this is the actual loop body inside both nested loops, right? And in this one, again, we can maybe do a quick check. It looks like we've got a comparison here. It looks like we've got an addition here. This is maybe one we might miss sometimes, but it looks like there's an addition there too. These are both J+1s. So again, if we're clever in our initialization, we might be able to get away with only doing that once. But here I'm just taking the naive approach that is embodied in our pseudocode and just assuming it is the way it is, meaning assuming that this is one addition and this is another one. Now, the last operation on this line is this swap operation. And here, this is actually a method call. And we need to be careful here. We're not really certain how many operations it's going to take for us to do the swap. The only real way for us to know is to go look at the swap. So most of us have probably written a little swap function like this before, and we know that a swap function will require a temporary variable, and we usually will do probably about 3 operations here. Now, at the very least, we do one copy, we do another copy, and then we copy back in again, and then we're usually done. Now, for our purposes right now, I'm going to plead a little bit of agnosticism here. I don't know what's going on in that swap operation. I know, though, it's probably a constant. I just argued it might be 3. It could be more, depending on if there are maybe +1s or -1s or things I'm not thinking about showing up somewhere in there. However, I'm going to count it all as just one operation. I'm going to lump it all together. And this is something that we haven't been doing up until now. And we probably won't do this very much more in these series of videos, except for maybe the swap operation, is that sometimes when we know that an operation is going to take a constant amount of time, meaning big O of 1, meaning some constant, maybe it's 5, 10, something like that, but not a variable, not depending on n. If it's going to take a constant amount of time, we sometimes just say, fine, we'll name that constant C. That's a very common thing we might do. Or, as what I'm doing here is even more severe, I'm going to say, let's just say that constant is 1, which is usually sweeping a lot under the rug. Now, why am I doing it here? Instead of going to count that swap operation, maybe I should go count that swap operation. If I find out it's 3, that might tell us that we actually had to take a couple more operations in this bubble sort. But again, for our purposes, for our analysis in this video, I'm going to just leave it at 1 swap. Okay. Now, after that line, this is again, whenever this line is carried out, it looks like we've got 4 operations here. Now we've got the exits. Now remember how we dealt with the exits before? I actually like that I leave them in here both as scope identifiers to see where the loop body is, and then also to remind myself that exiting a loop isn't always for free. At the very least, exiting your loop, you do another comparison, right? No matter what type of loop you're in, a while, a repeat, or a for loop, there's some comparison you have to do to see, should I keep looping or should I stop? Should I end the loop? And in this case, it's, for instance, comparing to n-1. And basically what that means is we re-execute this line one more time. We iterate back up, we increment the j, we do this subtraction because we need to, and then we do the comparison. And when we're done, it kicks us out. So that tells us we need those 3 extra operations again. And then likewise, for exiting this one, I just went up here and checked there's 3 operations there. So again, it takes me 3 to exit. And I'm going to assume it takes us 1 operation to return. All right, let's see if we can put this together. And usually we want to give it a name like f of n, and we want to count the number of operations carried out in this whole thing. Okay. Now, I'm just sort of going to go right as we go along. And the first line is 1 colon. I'm going to write it by itself because it's the only line, at least, before the sum or the loops that we're going to express in a sum. So I'm going to write this as 1, and then I'm going to start the sum for the outer loop. Okay. Now we're going to have, I think I mentioned this a little bit earlier, but we have 2 loops. So we're going to need 2 sums. And because our loops are nested, we're going to end up with nested sums. Okay, a sum with a sum inside of it. All right. Now we're going to do the outer sum first. And since it's going to have a sum inside it, I'm going to give us some big brackets here to keep track of all the stuff that's inside of it. But first, let's get its indexes set up. And as my variable of indexing, I'm going to use I because that's the same one I used in my for loop. And I'm actually going to be comfortable to just use the same indexes there. So my for loop says for 1 to n-1. So that sum is going to capture those n-1 iterations of that loop. Okay, so then we're going to push in, and now we want to count all the operations that are carried out only in the loop part. Okay, only in the loop part, meaning maybe not the exit and maybe not any extra operations at the end. I'll worry about that at the end. So inside the loop, okay, well, we've got another loop. Okay, well, let's worry about the stuff that happens before we get to the loop. And just like before we got to our first loop, all we did was enter the method. Before we get to our second loop, all we did was enter the loop. So how many operations did it take us to enter the loop? Well, it told us over there, one assignment the first time, right, when we set I equal to 1 the very first time. And then we do the subtraction and the comparison. Assuming n is big enough, that means we're going to punch into the loop. So how many operations was that? That was 3. Okay, then we enter the inner loop, and our inner sum is going to have j as its counter now. Just like in code, if you've got 2 for loops, you want to, especially nested ones, you want to make sure you use different counters so they don't interfere with each other and mess up and get a bug. It's the same thing in math. If we have 2 variables, we don't want to confuse them, so we'll give them different names. So, and of course, we've already used 2 different names in our code, so why not borrow them? So again, we're going to go from j equals 1, and let's be very careful here. The upper bound is now going to be n minus I, not this minus 1. We're going to get I up there. So this is really important to have this nested sum like this, because the upper bound of the inner sum is dependent on the variable in the outer sum, and that's, if it wasn't nested, we wouldn't know what I means, okay, in this context. All right, but now we've entered that inner sum. How many operations for the inner sum? So right now I want to look at just those 2 middle lines, because those are the ones that we keep sort of doing over and over and over and again as we're in that inner sum until we exit it and then do one more iteration of the outer loop instead. So those 2 lines in the inner loop, those are the ones that we get to do over and over again. How many operations on those ones? Well, it looks like we got 3 on the first one and 4 on the second one. Remember that 4 is where that swap is, so maybe that 4 isn't exactly right, but let's call it 3 plus 4. What is that? That's 7. And then what else do we need to consider? Well, remember what we're doing right now is when we're done this inner loop here, we still need to exit it, and that's this n4 that we say has another 3 operations on it. Now once we're done that 3 operations, we might go right back to the beginning of our outer for loop, right, which is do another 3 steps and then do another inner loop here. So I think we've captured our loop there. The only thing we forgot is we still need to exit the outer loop, and that looks like it's another 4 operations here. Okay, if you're keeping score in the back and you thought, hey, I want my swap to be more expensive than 1 operation, I didn't like that argument he gave me, well, that 7 maybe is misrepresented here. So let's do a little math here. Let's say our swap was 3. I think 3 is what I said, and that makes sense, not counting maybe the method call and the exit. Let's at least call it 3. If it was 3, you might get 9 there instead. If you want to count the method call and the return from the swap as well, so maybe that gives us 5 operations over there. Oops, I was going to say plus here. We could also maybe swap that out with an 11 as another possibility. Okay. Now the reason I want to just highlight this now, I'm going to leave the 7 in there because, well, that's what I've got on my slide, so I want it to match what we've got. But when we go through, let's go through and double check, or maybe at the end we'll just sort of follow this 7. It's gonna creep its way through and show up here and there, okay? And when we're done, we'll say, hey, what would happen if we change that 7 to a 9 or 11? Sometimes that 7, especially if it was, say, out here, changing this 4 isn't going to do much. If we change that to an 11, at the end of the day, we're probably just going to throw it away. Okay, the big O or the big O proof that we do, this will probably end up being a lower order term and we'll throw it away. But I'm guessing this 7 is probably going to make a bigger impact. So we'll keep an eye on that as we go. So sometimes when you've got your runtime analysis at this stage, when you've just sort of looked at some pseudocode and written it down, it looks a little bit messy like this in the sense that you haven't really gathered all your terms together in a way that sets it up for easy simplification. The first thing I'm going to probably do is I'm going to gather this 1 and this 4 at the end here together. Why not? They're 2 constants, right? And the other thing I'm going to do is I'm going to write them first. Even though that's a constant and it's probably going to end up being my lowest order term, And we usually leave those to the end. Because I've got sums in how I'm writing it, and it gets ambiguous if you write a +4 after your sum. Is that inside the sum or outside the sum? Unless you throw these big brackets around it, right? For instance, this, what I've written right here is ambiguous. Do I mean the sum just around the 7, or do I mean the 7 plus the 3 is inside that sum? Because of that ambiguity, we tend to write anything we're adding on to a sum out front instead of out back, and that way we can write the sum next. So I'm going to write my sum next. I equals 1 to n minus 1, and then I'm going to do that. Because I have two things I'm adding together inside this sum, no matter what, I need to put them, no matter which way I put them, I need to put them inside some big brackets here. So I'm going to put them inside the big brackets. But I am maybe going to gather my 3 and my 3 together and make it, let's call it a 6. I am going to put it out front. I don't know if I necessarily left myself enough room in here, but I got myself a j1 to n minus I. That's copying that one down. What do we have in there? A 7. Okay, the 4 came out front to the 1 to make a 5. The 3 came out front with the 3 to make a 6. Okay, so what do we do next? I'm going to maybe do it here just to save myself a little space. The next thing I'm going to do to simplify is I'm going to try and simplify my inner sum first. And this is commonly the strategy that we want to do. Okay, there's actually a couple steps I could do here, but I'm just going to focus in on the inner one because it doesn't depend on the outer one. The outer one depends on the inner one, but the inner does not depend on the outer, other than this term I here, so it's easier to solve the inner one. Okay, so let's leave the 5 alone. And what can we do with that inner sum? Well, I'm going to be maybe step by step here. We can first factor that 7 out, which leaves a 1 on the inside. Now what can we do with this sum inside? Well, once we get a sum down to just being a sum of 1, we have a simple rule, and maybe I'll just quickly jot it up here. If we have the sum from a to b, our a happens to be 1. If we have the sum from a to b, we get b minus a plus 1. Or even simpler, when the bottom one, our a, happens to be a 1, I put a j in this case, I guess, of, oops, I wrote that wrong. That's what I meant here. If our j was a 1 at the bottom and we have some kind of b at the top, the sum of that is just b. So obviously this sum here is determined by its upper bound, which just happens to be this n minus I, meaning this whole sum here just turns into n minus I. Okay, so we can continue moving now. I'm just going to do on my next step, just distribute things out a bit. I'm going to maybe multiply that 7 through. And then I'm also going to recognize that I can distribute this sum over my 3 terms here. Okay, the first one we're going to get I equals 1 to n minus 1. They're all going to have the same bounds, but the first one is of a 6. Then plus, we're going to get the next one will have 7n as the term, so we get another sum of 7n. And then we'll get a final sum here of our I, but in this case it was actually minus 7i. I'm bringing the 7, or the minus, out front here. Eventually I'm going to bring the 7 out there as well. In fact, that's the next step I'm going to do. So let's do one more step. We'll have the 5 carry it down. And now I'm going to factor out anything I can out of these sums. So the first sum, 6 doesn't depend on I, so I can factor it out. In this case, the 7 and the n do not depend on the I, so I can factor them out. And in this case, well, the 7 doesn't, but the I does. The I has to stick around where it is. Okay, so now that we've factored those out, at least these first 2 sums are easy. This one might be easy if you remember what it's equal to, but these first 2 sums are easy in that, just like the one we had up above here, this is just a sum of 1s, and we just need to look at the upper bound. So we've got here 5 plus, so our upper bound here is 6, or sorry, is n minus 1, so we've got 6 n minus 1 plus, same thing here, our upper bound is n minus 1, so we get 7n, n minus 1, And then it looks, well, I'll just leave this one alone. We'll deal with it after on the next line. Okay, maybe I'll just simplify out these earlier terms a little bit. We've got 5 plus it looks like 6n minus 6 plus it looks like 7n squared minus 7n. And now what do we do with these terms here? Well, this one, remember this sum, that's a pretty ugly sigma, but let's roll with it. This sum, if we go with just I equals 1 to n, is equal to n times n plus 1 over 2. I call this Gauss's sum. This is also known as the arithmetic series. This one, I usually just, I've got to the point where I just know this one. If I forget it ever, I just remember Gauss's proof. But we don't have this sum. We have a slightly different one. We got this one. What do we know about this one? Now this one, again, I know it because I remember the other one, and I remember that, hey, if I change this to n minus 1, that plus changes to a minus. It's math-magic. If you want to go prove it to yourself, you can. You've got the tools to do that if you want. Go verify that that's true. But if we do raise this just up to n minus 1 instead of n, we get a minus in there. So that's what we're going to get. We're going to get minus 7 times, and then that whole value over there, n times n minus 1, because we have an n minus 1 as our upper bound, all over 2. All right, we're almost done. We're not quite there yet, but we're almost done. Now it's probably a good idea to start gathering some like terms. And maybe I'll be careful on these ones over here. Let's start with our squared. We have 7n squared here, but we have minus 7n squared, but divided by 2, so half of a 7n squared. So that actually leaves us with a half of a 7n squared. Okay, so I did this one and, well, that one. Okay, so now I'm going to do a plus. That's wishful thinking, hopefully, because I'm going to do the n's now. Okay, and here we've got a 6n. Here I've got a minus 7n, so it looks like here we're already at minus n. And then here, oh, I need to be very careful. I got a minus 7n, but that's another minus in there, so that's a plus 7n, but it looks like it's a plus 7 halves n, which, just a little bit of math, gives us 5 halves n. So I think that's my next one, 5 halves n. And then it looks, okay, so let's be careful. That was this n, this one, and that last bit. And that left us with what? Our 5 and our 6. So it looks like 5 minus 6 is minus 1. So I feel like, most of our instincts probably, if they're kicking in now, already know that this is going to be a big O of n squared, or more precisely, big theta of n squared function. But we can actually do that with a very quick limit test. So let's try the limit as n goes to infinity of, let's see what we have here, 7 halves n squared plus 5 halves n minus 1 all over n squared. Computing the fractions, we're going to now get 7 half plus 5 over 2n minus 1 over n squared, which hopefully we can see, not too much effort, it's going to be 7 halves after these two go to 0. Which, remember, a constant, a non-zero constant, means that the theta relationship is what we found. So we got the right guess if we were just guessing our n squared here. But hopefully it wasn't a guess. Hopefully you're just reaching into your intuition and saying, hey, that's the highest degree, and I know that's the bound that we're going to find. All right, so I just want to finish up by sort of noting, going through that one more time a little bit quicker, and noting that we did, I think, go through some of the same steps. So it looks like here, our original sum, we gathered them together. It looks like I factor out the 7. We did the same simplification. I think we got to this same sum here. Again, we factored it out. We simplified, and yes, this looks like what we got when we were working together. We had this final sum here. We computed it using Gauss's formula. And let's just double check. It looks like we got ourselves into the right same final function. So that's good to see. That means we didn't make any errors in our math. And the other thing I want to verify here in looking at this again is, remember what I said about our mysterious 7. We said, what if we got that wrong with that swap? In case you were, again, keeping score or keeping track. What if that was a 9? What if that were an 11? Well, the interesting thing I think we'll end up here is we can see that the 7 trickles down, it duplicates itself here, it shows up in a couple of places here. It's now, quadrupled itself here. And maybe this is the last place where we can see them all clearly. We're going to have maybe a 9 halves here or an 11 halves here. Okay, and same thing here, we might increase this to a 7 halves or a 9 halves here. Which is the bigger or more important change? And I hope you're leaning towards this one. And this is probably more important, right? If we end up having 9 halves n squared or 11 halves n squared, that's going to make a bigger impact. Now, the other side of that coin, and I think part of the reason why I am not as concerned that I didn't get that right, when I counted it as one swap, I don't feel very concerned. And if you are a little bit more concerned, maybe you can share with me this intuition. Even though that it impacts the ultimate formula, the ultimate function that we have to express the runtime, and if you're an engineer and you care about nanoseconds, then you might want to shave a 9 halves down to a 7 halves. But as we saw with our limit test here, if we change this 9 halves or this 7 halves to a 9 halves or an 11 halves, our conclusion about the runtime as a asymptotic bound, its growth rate, is still n squared. And this is why you might find, as you get more experience with algorithm analysis, that you'll find as you read other analyses out there that we tend to just throw these constants away. Or if we don't throw them away because that's a bit sloppy, we might just start giving them names that are not 7 halves, because that's too precise to keep track of. We'll just call it C. And then when we start adding C plus D plus E, we'll just call that one F. So we don't have to keep track of which constant it is, just that it is a constant. And that's because most of the time, from the asymptotic perspective, which constant it is doesn't matter. Okay, but that, on every coin has a flip side. If you're an engineer, then you're going to start saying to me, yeah, but I care what that constant is because it's going to run faster or slower on my machine. And I think that's a very valid perspective as well. Okay, and just like I've been saying with a lot of the things in this series of videos, the reason why we're going to use a particular tool depends on the purpose that we're trying to serve. So we have some goal in mind, and that's going to determine whether we're going to care about those constants or not, ultimately. Okay, well, that's all I wanted to do for the runtime analysis of bubble sort. In the next video, we'll do the same thing all over again, but with selection sort. All right, so thanks for watching, and we'll see you in the next video.